Hi everyone, welcome to this continued series on understanding sense of data and pre-processing steps. We have covered quite a few pre-processing techniques in machine learning or prior to machine learning. In this video, we will look at few more techniques. In the previous session, we looked at scaling and then encoding of the categorical variable. In this video, I'll be touching upon the data imbalance and the problems with data imbalance from the machine learning perspective. Data imbalance in machine learning or data science refers to a situation where the distribution of classes within a data set is significantly skewed. That means one or more classes having more number of samples compared to the others. And this imbalance can pose problem when it comes to machine learning algorithms, particularly those which are designed for or where we expect high accuracy and consistency and generalization. As the reason is, if one class has more number of samples compared to the other, then machine learning models typically get biased towards the majority class and doesn't recognize the distribution of data or patterns in the minority class. So it's very important to understand the data imbalance from machine learning and deep learning perspective. Let's get started here. How do we so the scope of this discussion in this video is going to be a general idea. So we'll try to understand what is imbalance and what it is and how do we find out the imbalance in the data set. We are not going to talk about how do we address the imbalances because typically that will require machine learning models to generate new samples. Even the modern generative models that today we are talking about GPTs and transformers and BERT and autoencoders and so on and so forth. These are models designed for generating or compensating for the minority class. So we're not going to talk about how do we address using various machine learning models, rather keep the discussion short and limited to just understanding of the problem of data imbalance from the data pre-processing perspective. So let's define data imbalance. It's quite simple. When the distribution of data across the classes is uneven, in that case, we say that data set is imbalanced. And handling data imbalance is important because it can lead to the model performance being biased towards majority class and ignoring the minority class. So let's talk about how do we identify class imbalance. It is little subjective and requires domain understanding as well. But identifying data imbalance is quite simple. Count the number of instances in each of the class. If one class is really significantly higher in terms of number of samples, then you know that the majority class is dominating the minority class. Or in other words, we can, instead of just looking at the number, we can compute a few ratios. So one of the ratios is class proportion ratio, where the number of instances in the positive class, let's say 100, and the number of instances in the negative class is 500, and that gives you the ratio of 0.2. That means for every so this means for that the positive class is or underrepresented compared to the negative class. We are looking at the value which is like, close to 1 would be ideal, but practically that's not going to be the case. Even 0.7, 0.8 would be good. Imbalance ratio is another way to look at it, the number of instances in the negative class and divided by the positive class. So this gives you just the inverse of this. So that means you can say one class is 5 times larger than the other. So depending on your comfort, you can use any of these metric. Techniques for handling data imbalance, as I mentioned, there are very advanced machine learning models that are used to handle data imbalances. In this video, I'll show you some simpler methods here. So resampling technique is the one that I'm going to show you. How do we resample? Ensemble method is advanced machine learning methods. Data augmentation is also through advanced machine learning like deep learning methods. We generate new sample and thus we compensate for the lack of data in the minority class. Transfer learning is another technique, which is a modern day technique rather. Using a pre-trained model, you can generate new samples. Generating synthetic data is statistically, this is one of the most popular, most common, and also very old method of generating, or compensating for the lack of data. So naive random oversampling is a method that I'm going to show you. This method is just to give you an illustration as to what is imbalance problem and how do we deal it. In practical projects, you're not going to use naive random oversampling. This is just for illustrating the concept of data imbalance. This is naivest strategy to generate new samples, compensating for the lack of data in the minority class. Let's talk about how do we do so. Here is we have one class which is represented by 0, the other class is represented by 1. So this sample 0 is here and the remaining samples belong to class of 1 here. So you can see that this is a minority class. You have only one sample. Here you have 4 samples. So the objective is to replicate the minority data in such a way that you have equal number of samples. So here now you have 4 samples of 0 and 4 samples of 1. This is called balancing the data set. As I told you earlier, this is not how practically we will address the class imbalance problem. Another example is here. Here you can see here this particular data belongs to the class of 1 and there are class of 0 data, which is class of 0 data. Then you can replicate for the class of 1 in such a way the number of samples are the same here. But here just to take a look at it is randomly generating out of the known 4 samples is just randomly picking up the data in such a way that the count of 0 samples and count of 1 samples is similar or same. This is what we mean by saying, addressing the problem of data imbalance. Is random oversampler useful at all? Probably not. It is not useful. It can result in too much of duplication, and thereby it will introduce the risk of overfitting. Overfitting is again a machine learning concept that means that the model will remember the patterns, and that's not what we want. That is not the goal of machine learning, to remember the exact data or exact pattern. In fact, the oversampling, any of the oversampling technique that we talk about, even the advanced ones, we have the risk of overfitting. So random oversampler does not generate new information because it's simply copying the existing minority data, maybe replicating a few more times and then making the number of samples in the minority same as the number of samples in the majority. So that doesn't mean any new generation of or generation of new information. The idea of machine learning is to deal with uh, varied data and diversity in the data. So random oversampler does not generate any new synthetic data. In order to generate new synthetic data, we use models like SMOTE or Adasine. These are also quite common and quite popular methods, and also very old method. So the random oversampler does not address the data distribution gaps, means it's simply duplicating and replicating the data in the minority class number of times. So the data distribution problem still remains. So let's talk about SMOTE. SMOTE stands for Synthetic Minority Oversampling Technique. It's an oversampling technique which is advanced and slightly sophisticated. It generates something new, unlike the random oversampler. So, unlike random oversampler, SMOTE does not duplicate or replicate existing samples, but creates something new. And it is very interesting to see how it generates something new. We will look at that through some dummy example, how it generates a new sample. Step number one is to determine which class in the dataset has fewer instances. Generally, is going to be a minority class. The class that you want to oversample is referred as minority class. Step number two, after selecting the minority class, we will pick one sample in the minority class. It's randomly chosen. Now we will apply the algorithm called nearest neighbor algorithm. That means from the existing data set, we will pick the nearest neighbor for the randomly chosen data in the minority class. Okay, so this is again a machine learning model, but let me illustrate how it actually works. So let's say this is our rows, and this minority class. This is my minority class here, and this is my majority class. So what we're going to do is we will look at one of these samples in the minority class, and then let's say the minority class is 1000 samples, and then for the chosen one, so this is my 1000 sample, and for the chosen one we're going to find the closest two. Let's say the closest two is this one and this one. For this chosen one, let's say this chosen one is record number 1 or 111, record number 111, and the nearest neighbors are these two samples. Nearest neighbors means the sample is closest to these two other samples. This is what the meaning is here, the find the k nearest neighbor. And this k is configurable. That means it is another hyperparameter. That also means additional tuning effort. So we need to find out what's the optimal value of k for our data set. Usually it's taken as 5 or 3. So based on that, the default is 5, and we use the 5 neighbors to proceed. So now after we have found the neighbors, we have to generate the synthetic instances. Now what we do here at this step, for each neighbor, the synthetic instance is created by the synthetic instance is the new data. Okay, so that's my new data. This new data is created by calculating a vector. Vector is simply a record or a new record in this case between the selected instance from the minority class and the neighbors. Sorry, this should be neighbors. And I'm going to show you how it is done. After the vector is chosen, we randomly multiply here by some scaling factor. This is also configurable, typically taken as zero point 0.1 or zero point 0.2, but you can configure this. And after the multiplication, the scaled vector is then called the new record, and this is added to the selected instance to generate the new record. So let me illustrate what this all mean with an example. Suppose we have a minority class A and there are two columns XA and X and YA, and the value are like 3 and 5. So that means this is a record. 3 and 5 is a minority instance. Let's say the neighbor is 2, number of neighbors is 2, and the algorithm has found the two nearest neighbor of this particular instance in the minority class. That means you're going to find the neighbors from the minority class, and those neighbors are, for example, are 4 4 and 2 6. So for this one we have these two as neighbors. Now we are going to generate the synthetic data or synthetic instances. Let's see how we do that. Let's take it forward. So now the step is to generate the synthetic data. Now what we do is compute the vector BA. So what was A? A was our minority instance here, and B was the neighbor. Similarly, A is the minority instance and C was our neighbor. So now what we're going to do is pick the value and just subtract here. Okay, so it's basically finding the vector. So what we're doing is simply, if you take a look at it, what exactly we are doing here is, let's say this is A and this is B. So we're just subtracting this and finding, you know, the new vector. So 3 minus 4 and 5 minus 4. So that's going to give you a new vector. Similarly for CA, we're going to repeat the same thing and we're going to get the new vector. Let's see the next step, what we are doing here. The next step is scaling. So now we have to scale it. Let's say our scaling factor is zero point 0.3. You can configure it. So zero point 0.3. So we simply then multiply here the scaled vector BA that we computed earlier is going to be multiplied by zero point 0.3 that we with the vector that we computed early on. So zero point 0.3 multiplied by this, zero point 0.3 again, multiplied the other vector, and then you get a new scaled vector. Notice how we are, how the process of generation, this is like, we are trying to generate new sample, very related to the existing sample. So it's pretty close to the existing sample. The synthetic instance one, so now we are generating new data. Let's say, we generating two synthetic instances or two synthetic uh, records. So that's instance A, and then whatever scaled vector that we computed earlier. Simply add them. Now we got new data. This will be added to our minority class. So this is the basic idea of SMOTE, and the SMOTE process will repeat for all these samples in the minority class. So there's quite a bit of configuration that is required in the algorithm. So when we come to machine learning and when we deal with imbalances, I'm going to show you how to use the SMOTE algorithm in scikit-learn or Python. So essentially, we repeat the process, repeat it for specified number of times or until the desired level of oversampling is achieved. This is also configurable in the algorithm. Thus completes your typical workflow that is done in the SMOTE algorithm. The synthetic instances that we generated are new instances generated for the minority class. In a more realistic scenario, the feature space would have more dimensions. I mean, I showed you with just 2 column. In the real world, it will be 200 column, 300 column. And that means the process would be pretty involved. And the SMOTE algorithm is designed or probably written in C++, and that's how it handles the high dimension data and does the vector addition, computation, subtractions, and all of that. The idea is to create diverse synthetic instances around the minority class. So this completes our discussion on synthetic on data imbalances. Now, when we come to machine learning, I'm going to show you the handling of the SMOTE algorithm. But for now, I'm going to show you random oversampler method in the Python or using simple Python and a scikit-learn. So let's take a look at the random oversampling. You have to install the package Imbalanced learn, and that has random oversampler. And let's say this is the same data set that I showed you in my presentation earlier. So this is a minority class, belongs to class of 0. And then you pass it to the oversampler and fit and resample. Quite simple. Provide X and Y. And after that, you can take a look at the resample data. You have replication. Means the same value is being repeated many times because just because you have one sample in the minority, so is duplication. Let's look at another example where we have slightly different data randomly generated here. So it's like this. So this belongs to one class and the remaining would be another class here. That's my original data. The first 4 data points are one class, a minority class, and the remaining are majority class. Again, we call random oversampler and fit and resample the provide our data. And then after that, you can see here is the original data. This is also original data. And after that, randomly, it has picked up the or replicated or duplicated the data from the minority class. Now the number of samples in minority and majority are same. So this is just a basic idea of oversampling technique used to make the minority class similar to majority in terms of number of instances. As I mentioned again, this is not really practically used. The more practical usage is to use advanced models like SMOTE, which I described in the slides earlier. So that was the coverage on data imbalances. Essentially, I wanted to talk about the severity of the problem and some standard rudimentary methods to handle imbalances. More advanced methods for handling imbalances I'll be covering in the machine learning sessions. The next topic is going to be data splitting. After a lot of pre-processing, we have to prepare our data for machine learning. Thank you all. Have a great day. We'll see you in the next session.